Okay, so we've seen now our candidate construction of obfuscation, right? We took a matrix branching program. Just reminding you again, remember the colors correspond to the inputs, right? There's the first bit, which is the blue input, the red input, the green input, and these matrices always cycle. They're, blue, red, green, so on and so forth, right? And what did we do? We took the matrices, we Killian randomized them, we added these straddling sets to make these sort of puzzle pieces, which is the place at which we're applying the multilinear encoding, right? And then finally there was this little alpha that we added, okay? So, so far all I've claimed to you is that we don't know any attacks, okay? Let's see how we can try to get more confidence in security, okay? So the first thing I would like to do is just rule out algebraic attacks. So what I mean by an algebraic attack is an attack where the adversary respects the multilinear map framework, right? So the only thing he's allowed to do when he has an encoding is add at the same level, multiply across disjoint levels, and test for 0 at the final level. That's all he's allowed to do. Aside from that, he has actually unbounded power. He can do whatever he likes, but those are the things that he can do. Okay? Yeah?
So the attacks that Sanjay talked about, do they fit in the multilinear?
No, absolutely not. No, they absolutely do not. In fact, these are kind of generic attacks that we're talking about right now. We will talk more about more standard notions of provable security towards the end of the talk. Okay? But I wanted to start small. Let's think about algebraic attacks. Okay? First, I just want to mention that even these algebraic attacks, these are kind of generic attacks for people who have looked at generic bilinear proofs and generic DDH style proofs. Yeah.
I want to ask. So I really like this description from the
BGKPS.
For preventing the attack of choosing. What did you have in the GGHRSW?
Yeah. It was kind of similar, but instead of doing it at the level of the multilinear map levels themselves, we did it with these sort of multiplicatively. We did it multiplicatively. Like it was actually very similar structure, but it was done at a multiplicative level within the encoding itself. So at a very high level, the idea was actually very similar, but it was executed in a different way. Okay, so I just want to just briefly mention that algebraic attacks here are really interesting, right? In fact, there's an entire subarea of complexity theory, arithmetic circuit lower bounds, right, which looks at trying to prove that certain arithmetic circuits cannot compute certain functions, right? And there are lots of cool open problems in this area, right? And the kinds of questions that we're asking now are actually related to that. In fact, in a certain model, not exactly the model I'm talking to you about right now. This is in a work with Eric and more. In fact, there are some obfuscation-related security conjectures in this generic sort of algebraic setting, which would actually imply the analog of P versus NP in the arithmetic circuit complexity scenario. They would show that VP is not equal to VNP. So it's actually more interesting than it might first appear. I think, yeah?
How different is it from the generic group model?
So its modeling is identical to the generic group model. I'm not going to get into all the details of that right now. But the main difference, again, is that it has to support multilinear operations, right? That there's a generic oracle, and you can ask it to add, anything you like. It can ask it to multiply as long as there's a disjoint set.
Encodings for a given element. So.
That is not being modeled. That's a good point. That's an excellent point. So there's lots of stuff that Sanjay was talking about that we're not modeling here. And again, this is just this is the initial step because we want to first gain some confidence. And personally, I think it's very important for us to establish confidence in this way because it's such a new area, right? And we want to understand what the limits are and what the different freedom of actions that we have here are.
So there is a meaning of this multiple.
Sorry?
There is a model of this multiple encoding there.
We can also do that. Yes, there are various ways to strengthen the model, but that's not what I'm talking about to you today. Today, I just want to think about the very simple model where, you can think of it in terms of a handle. That the adversary can say, okay, see this matrix entry here, see this other one here. I want you to multiply them, and then the oracle tests: are they at disjoint levels? Yes. If so, it says I multiplied them, and I give you a handle for the result. And then you can use that handle and do whatever you like. This is this sort of very black box way of thinking about the problem. Okay.
Yeah. Can you say some more? How is it connected to arithmetic circuit complexity and VP versus VNP?
I could say a little bit more. Okay, so what we're doing here is most closely related to multilinear lower bounds, which Ron Raz has some beautiful results on multilinear lower bounds in arithmetic circuit complexity. But if you extend the model further, which is what we did in this other paper, where you allow the adversary to even go beyond what he should be able to do in the multilinear model, but which is algebraically feasible given all the representations we have, then that naturally leads to a model that's essentially equivalent to arithmetic circuit complexity, proving the lower bounds there. And there's certain specific conjectures that we can make that would imply VP is different than VNP. Yeah.
So, when you talk about obfuscation-related security conjectures, you mean for these particular techniques, right?
For these particular techniques, yeah. We also have some moral arguments, but nothing extremely concrete. Some strong moral arguments, actually, to show that. So any algebraic construction of obfuscation that meets certain sort of sanity conditions that all current obfuscation candidates do meet, if you could prove that they are VVB obfuscators, then that would imply that VP is not equal to VNP. But there are some sanity conditions and things like that that are involved. I was lying to you a little bit there, but I can tell you more maybe in person, or Eric can also talk to you about it. But there's good news. Anytime you say, hey, we're like these complexity theorists, we should all start to feel very sad, right? Because complexity theorists have a very hard lot in life, right? And if we had to do what complexity theorists have to do, that would be very bad. And so the good news is that unlike those poor complexity theorists, you know who you are in the audience, those poor complexity theorists, they have to study, or they're supposed to study, right, the algebraic complexity of natural functions. But we're cryptographers. We get to make our own crazy functions. And as long as they're useful, they're good enough for us, right? And that's really going to be critical here. The fact that we can make our own crazy functions, and the craziness here will have to do with these jigsaw puzzle pieces, right? We're going to assemble these things in a certain way that makes these arithmetic complexity arguments easier to execute. Okay. All right. So I want to give you a proof. First of all, what do I need to do? What does it mean to prove that a scheme is an IO scheme? So recall that the definition says that if you have two equivalent circuits, C and C prime, then the IO of one should be indistinguishable from the IO of the other, right? This is actually equivalent to another way of thinking about security. And this is to say that there exists an unbounded simulator, a simulator that runs in unbounded time, and that can make unbounded number of queries to the circuit C. Okay, so it's given the circuit C only as an oracle. It can make as many queries as it likes. It can write down the entire truth table of C in particular, right? And if such an unbounded simulator exists that can simulate any polynomial time adversary that's given the obfuscation as input, then this also is an equivalent definition of IO. Okay? Let's think about that for a moment. It's actually very easy to see. Why does this definition imply IO? That's completely straightforward, right? Because if the simulator has C as an oracle, or if it has C prime as an oracle, that's the same oracle, right? These are equivalent functions, right? So the fact that IO, so we were already assuming that the output of this is indistinguishable from IO of C, and these are just the same, and this is indistinguishable from IO of C prime, right? So the fact that this implies IO is triviality. The other side actually follows from this observation we made earlier, right, about if P equals NP. So the other side is just, an unbounded simulator can write down the entire truth table of the circuit and just construct the padded minimum circuit, right, for this. Call that T and just run the obfuscator on that and output that, right? So this shows that IO implies this definition, okay? As it turns out, this unbounded simulator definition is the easier one to work with when we're trying to prove algebraic resilience against algebraic attacks. Okay, so how will we do this? What do we need to do, right? I need to give you a simulator, right? What does the simulator need to do? The simulator is talking to an algebraic adversary, right? The adversary can build polynomials of its choice, right? It's given these elements, these encoded elements of all those matrices, right? And it can take one piece, it can multiply it by 2. It can take another piece and multiply it by another piece. It can do all these kinds of things, right? And in that way build some arbitrary polynomial. If that polynomial ends up living in the final level, right, in the level 1 through k, then he can ask, hey, is this polynomial 0? Right? And the simulator has to answer him. Before that, the simulator doesn't have to do anything. He says, hey, I want to do this and this. Great, you got another handle. He just keeps handing out handles, right? He doesn't have to say anything. The only algebraic operation in the multilinear framework that actually gives something in the clear is the 0 test, right? So the non-trivial question here is, how does our simulator answer the question, is this polynomial 0? That's what we need to do, okay? So let's think about that. Again, we have an unbounded simulator. So it can construct this polynomial in its entirety, right? It can look at every single monomial that exists in this polynomial, okay? The heart of the proof is the following. Because of this straddling sets, in fact, you can make a stronger version of straddling sets. That's what we do in the paper with Moore and Eric. We can prove that any such monomial can only touch matrix entries that correspond to a single input, right? Because if not, then these pieces wouldn't fit together, right? You wouldn't ever been able to get to that final level, right? And that's really the key. So, right, again, it means if I'm looking at some monomial, it's some elementary multiplication that's led us to the final level. We know the only way you can get to the final level is by picking up all of the pieces, right, that correspond to a single input, which means you've now got a single input x that corresponds to that monomial, right? So we can map, the simulator can map every monomial to its unique input corresponding to that monomial, right? Okay? For each such input x, let's think of P sub x to be the sum of all the monomials that correspond to that particular input. Okay? So our P is the summation over x of P sub x, right? And again, our simulator has to answer, is P 0? Okay? Here comes our, okay, in just a moment, we'll get to the alpha. Sorry. Okay, let me suggest that let's think about a simpler question. What about P sub x? Can we figure out if P sub x is 0 or not? Okay? And that we could do thanks to Killian, right? What we can do is P sub x corresponds to a single input. We know what the product of all these matrices. That's just going to be the output of that function on x. The simulator can go to the oracle, ask, hey, what's C of x? It gets the answer. It then applies Killian's simulation to simulate all of these matrices, right? It now has concrete values for every single element of these matrices. It then just plugs it in to P sub x, and sees, does it evaluate to 0? by the Schwarz-Zippel lemma, because this is a degree-bounded polynomial, we know that with overwhelming probability, if this polynomial is a zero polynomial, then we'll get the answer 0. And if we got the answer 0, then this polynomial is a zero polynomial, right? So here we use a Schwarz-Zippel lemma in a critical way. But so far all we've done is decide if p sub x for some given input x is the zero polynomial. We then need to decide, based on that, whether p is a zero polynomial, right? P is a summation of all these p sub x's. I claim to you the only way that p can be 0 is if every single p sub x is 0. Okay? Why is that? It's actually very simple, and that's where this alpha comes to save us. Okay? What is this silly alpha doing? Right? Alpha sub ib. All it's doing is introducing an independent variable for every setting of the input. Right? What that means is that if I have p sub x and p sub x prime, these are going to be algebraically independent because they have some alpha not in common with each other, right? So as formal polynomials, the summation can only be 0 if each one is individually 0, just by algebraic independence, right? So in this way, for p to be 0, again, just applying the Schwarz-Zippel lemma, it must be the case that each p sub x is 0. Because there's no way you can cancel out this alpha for px with anything in px prime for a different x prime. Okay? And that is the proof. That's the way the proof goes. Of course, most of the hard work is here, which I'm not getting into the details of. Okay? So this is how we prove security against any algebraic attack for I/O. I haven't talked about VBB. This can be strengthened to actually show VBB security as well. But for I/O security, this is what we need to do. Okay. Any questions on this? Yes.
So to invoke the Schwarz-Zippel, you need to walk over a sufficiently large field, right?
Yes.
So there is a blow-up, which is, regardless of the multilinear maps that will be perfect and very efficient, it seems that you have some blow-up which is related to the depth of the circuit or to the degree of the polynomial.
This is absolutely true. Yes, we do need our n to be a product of very large primes. Definitely, that we need that in order to be able to apply the Schwarz-Zippel lemma here. Yes.
I also have a philosophical question, another one. If this proof can be extended to VBB,
Right.
and VBB is not possible, isn't that a comment on the value of the proof as not really meaning anything?
So that's a very natural question, and it's hard to give a completely convincing answer in either direction here. But my personal viewpoint is that it is still very meaningful. Number one, just because it better be true, right? If you construct a scheme and it has an algebraic attack, well, then you're screwed, right? So, so this is at least as a sanity check, it's important to do this, right? The other point is that what does a non-algebraic attack mean? It means that you're using something more about the specific way in which you're implementing the multilinear map. And indeed, there are non-trivial attacks on multilinear candidates which are not algebraic, right? That has to do with some weakness in the underlying multilinear map. And that's something that's not considered here, just in the same way as any generic proof is, right? So my point is this: the weaknesses that are there in this model, I think, have more to do with the weaknesses that are always there in generic models, rather than having to do with this actual apparent contradiction, because that apparent contradiction just has to do with the bit level encoding of the multilinear of these encoded elements.
Can I add to that?
But yeah.
So it's like, think of random Oracle model. So we know it's not necessarily meaningful. Random Oracle. We have examples where you have security in the random Oracle model, but the scheme is broken. Still, having proofs in random Oracle model are not useless.
That's an excellent analogy. That's what I think that's really right, because again, there we have negative results as well, right? For certain functions.
But
Yeah.
the generic group model is different, right? So, for elliptical groups, for instance, I mean, there are no non-generic attacks. That's why it's one reason we're comfortable assuming the generic group model, right? But
Right.
here there are non-generic attacks.
Well, hold on. So again, just to be clear, that's actually false. So for elliptic curve groups, there has been a whole, research industry over the past several decades where there were proposed elliptic curves for pairings that turned out to be not secure because of these kinds of attacks. The point is, with multilinear maps, right now,
for which the best attacks not for discrete dominance.
exactly, just like CLT15, right? So in multilinear maps, as of May 19th, 2015, at whatever time it is right now, there are no non-generic attacks known, right? So the point is that that's where we are, and we want to be in a better place, but that's where we are right now.
I think you demonstrated there is a proof in the survey. It's not that we're going to believe that. Sure.
Right, and then of course there's a philosophical point. Anytime you have a proof, you understand something better. I think this proof helps you understand what's going on, and that's why, fundamentally, whether it's true or false, whether the thing actually exists or not, it does exist in this generic model, right? And that's a mathematical statement that we can be proud of and go home and get some good sleep, regardless of whether it's broken in real life. So, all right. So that is algebraic proof of security.
So where is the simulator using the superpolynomial power?
In this proof, in many places, by the way, that's not essential. So we can give a VBB proof, which means it can be all polynomial time. But the way that I described it, I wanted the simulator to consider every single monomial, right? I wanted him to take the polynomial p and unravel it as a summation of 2 to the n different polynomials, right? So I was using it in many different ways in that way.
Is it much more difficult for the polynomial time simulator?
Actually, it's this step right here that you have to make that effective. You have to be able to take a polynomial that the adversary made and extract out the input from it. It can be done. We did it in BGKPS and then in other settings as well. So,
yeah. So I just wanted to comment that random oracle model, generic model, all this stuff, basically it's impossibility results for the cryptanalyst.
Yes. Right. Exactly. Yeah. That's an excellent way of thinking about this. Yeah.
Hash function you cannot do.
Right. And here also you have to find some weakness in the multilinear map implementation intuitively, which is what people have been doing and what we should all be doing. And yeah. All right. So this is an algebraic proof, right? A proof against algebraic attacks. What about basing security on a natural kind of concrete candidate assumption in the usual Goldwasser-Micali sense, right? The way that we all know and love in our community. So I'll talk to you now about another result where we are able to base security with a reduction on a natural concrete conjecture. This is joint work with Craig, Allison, and Brent. And this is the second in a line of work, well, 2 papers in a line of work on building security proofs for I/O. There was an earlier work by Pas, Seth, and Telang on using a sort of Uber or meta assumption about multilinear maps to build I/O. But I'm going to talk to you about this more recent work. So. Let me first just change our setting a little bit, actually to go more like what Sanjam was saying earlier. Let's, instead of thinking about these non-empty subsets, let's just think about these levels, the way that Sanjam was describing them, right? So now I just have level 1 up to level k, just coming up in a nice ladder, right? Where each GI is a copy of Zn, okay? And we're going to think of this n as being a product of many large primes, okay? This doesn't make sense anymore. There's no such thing as disjoint numbers. So here we go again just to what Sanjam said, which is that if I'm at level I and level j, then I go to I plus j. And it's only allowed if I plus j is less than or equal to the maximum level k. Okay? So once we're in this setting, now we can describe a concrete assumption over multilinear maps. Okay? And now, when we're in the multilinear setting, where the level of multilinearity is a polynomial, like something that's growing with a security parameter, then the assumption will also have to have components that grow with the security parameter. So all of the assumptions are take a little bit of understanding, so I'm going to go through it slowly. Okay. Let's take a look at a warm-up assumption where k equals 1. Okay, so this is no multilinearity here. I have a composite n with 2 large prime factors. One I'm going to call a special prime factor C. Another one I'm going to call a distinguished prime factor A1. Okay? So I can represent any x in Z sub n by its residues, right? X mod C and X mod A1. I'm going to think about it that way. Okay? What does this assumption give to the adversary? The adversary gets level 1 encodings of a random generator of every prime subgroup except for C. Well, there's only one, just our distinguished subgroup. So it gets, an encoding of 0, R1, right? Where R1 is just some random number, which is just a random generator on that side. Okay. Also, it gets another level 1 encoding, which we're going to call H1, which is just random in both R2 and R3. This is the H's are going to get more interesting shortly, but right now it's just a random element. Okay. And then what the assumption is stating is that it's hard for the adversary to distinguish between an encoding of a completely random element or a random element, or a random element only in the second subgroup. Okay? Only in the distinguished subgroup. For those of you who are familiar with bilinear assumptions, this is the bilinear subgroup decision assumption, right? Just stated in this language. Why is it reasonable? Well, what can I do, right? I just have a random generator here. I get my target element. I'm trying to decide, is it like this or is it like this? If I multiply it with this, then it still looks random. If I multiply this with this, it still looks random. So the intuition is that it's very easy to argue that there's certainly no generic attack on this. And that's why we hope this is a reasonable assumption. Again, the bilinear analog has been a mainstay in the bilinear map world for a long time. Okay? Yeah?
So the assumption is that you're getting both the generator and H1, and then you get one of...
Yes, exactly. Yes, you get both the generator and H1, and then you get an element named T, and you don't know whether it is of this type or of this type.
But in the second case, the GCD with the generator would be C, and in the second case...
No. So sorry. This is not. This is an encoding, right? So I'm assuming that the encoding prevents you from doing that kind of GCD. That would be terrible, right?
Well, the encoding is not the CRT encoding.
No. Sorry. Yeah, but the CRT is just my representation. So I'm never going to call that an encoding. This is my CRT representation. But the encoding is the Mmap, the multilinear map encoding. And you're absolutely right. That is exactly what we want to prevent it from doing. You shouldn't be able to do GCDs within the Mmap encoding. Okay, and again, you shouldn't be able to, right? If all you have are these generic operations, there's no way to do a GCD. Okay, so this is our warm-up assumption. Let's see what happens when we increase the multilinearity here. So when I go to k equals 2, now I have 2 distinguished prime factors, A1 and A2, along with my special guy C. Okay, and I'm again going to have random generators for both of my distinguished guys, R1 and R2. Now the H's get a little more interesting. The idea of the H's is that they're going to be missing one of the distinguished prime factors. So I'm going to get H1, which is missing A1, H2, which is missing an A2 component. Okay, we think of these as our elimination variables, because when you multiply something by this, you eliminate one of the subgroup components, right? But I'm only giving you the ability to eliminate one component, and the multilinearity level is 2, that's the maximum level. So again, it's easy to see in the same way that the previous one was, that this should be secure, at least in a generic sense. Okay, so this is the multilinear analog of this sort of subgroup elimination, of the subgroup hiding assumption. something that we call the multilinear elimination assumption. Okay. Again, just to make that point clear, right? I can now multiply this with this, right? But then all I've done is eliminate one of these two, which is already present in both, right? So I haven't zeroed anything that I haven't been able to zero anything out that wouldn't get zeroed out with the other choice of t. Okay.
So I mean, if
yes.
Apply zero testing for one level above the maximum level, then your
then this assumption would break. So absolutely, we're relying on the ceiling.
like exact,
Yes, on the exact ceiling of k plus of k. You know, you cannot go to k plus 1. If you go to k plus 1, then you could eliminate two of them, and then you would easily be able to distinguish. So that's an excellent way of just seeing like what is it that we're assuming. Okay, this is a strong ceiling assumption. You know.
So we give generators for everything except the first subgroup, right?
Exactly. Yes, except for the first subgroup. That's important. Otherwise, you would easily be able to distinguish, right? Yeah. Excellent. Thanks. Okay. So in the general case, we have a k-level map. We have k distinguished prime factors. By the way, we also throw in some polynomial number of other primes. They're not going to really show up in the assumption, except that we're going to give generators for them. Okay. And again, these HIs, they're random elements that are missing a component in A sub I. Otherwise, they're random everywhere else. And again, it's hard to distinguish something that's random in all of the A's and the special guy C, or just the A's without the special guy C. Okay? So this is the assumption that we call the multilinear subgroup elimination assumption. Okay? So hopefully, in the multilinear sense, it's a natural analog of the bilinear subgroup decision assumption. Okay? And I want to stress that this assumption, there are no attacks known as of May 19th. Using the latest proposal, the CLT. Oh, sorry, I flipped. Sorry about that. Completely unintentional flipping of names. For the CLT 2015 proposal for multilinear maps. Okay, but I do want to make something important. Make an important point. Now that we're trying to give reductions, I'm not in as nice a situation as I was earlier. Right? I need to be able to manipulate these objects to get other encodings. That's what my reduction has to do, right? My reduction is given something from the assumption, it's to muck around with it and give something else to the adversary, right? So here we do need to support re-randomization. Again, CLT 2015 does support it, so that's the good news for us. Okay. And now what we show is that under this assumption, we are, in fact, able to achieve indistinguishability obfuscation. So how will we argue that? I need to give you a sequence of hybrid arguments, right? That starts at an obfuscation of C0 and winds up at an obfuscation of C1. I'm just going to explain this at a high level. The details are fairly complex, but I'm going to give you the main idea of what's going on. So first, at a super high level, what's going on here? We're going to use several hybrid steps, okay, to switch between C0 and C1. And the main idea is to, again, come back to Killian. Okay, I still want to exploit Killian's randomization to move between C0 and C1 one input at a time. Okay, so I'm going to move from C0 to C1 one input at a time. That means I'm going to have to go over 2 to the n hybrids, which might seem scary at first glance, where n is the input size. But again, if we're willing, in for a mile. Okay, anyway. But we want to, for the work, we need to assume sub-exponential hardness. So if we have our multilinear subgroup elimination assumption, we're going to assume it to be sub-exponentially secure, which means we're assuming that it's 2 to the lambda to the c secure for some constant c, where lambda is a security parameter. But there's only a polynomial overhead for the multilinear map realization. Okay. Once we do that, then we can just choose lambda such that lambda to the c is much, much greater than n, right? And this will allow us to have enough security to go over 2 to the n hybrids and still have sub-exponential security left over. Okay. So that's our overall game plan. And there are some, again, moral arguments that something like this is necessary, but this is something that we haven't completely nailed down yet either. All right, so what is the overall reduction strategy? We're going to again work input by input, right? So the idea of the reduction is to isolate one input, apply Killian to move it to the other circuit, and then isolate the next input. Then apply Killian, move it over to the other circuit, then isolate the next input, and keep on doing this. That's the idea, right? So the idea is that we're going to have only a polynomial number of parallel obfuscations, okay, which are obfuscating potentially different circuits. And each parallel obfuscation is responsible for a different bucket of inputs. Okay? In the beginning, this bucket is full. It has all 2 to the n inputs. This is 0, 0, 0. Okay? But eventually we want to use this to make our way through it. And there are going to be 2 types of hybrid steps. Okay? In one type of hybrid, we'll just be reallocating inputs from one obfuscation of C0 to another obfuscation of C0. So the program is the same. When we reallocate inputs, we're not changing the program at all. We're just moving inputs from one bucket into another. Okay? This is the place where we'll use our assumption. Okay? The second type of hybrid is after doing many hybrid type 1 steps, when we've managed to isolate just a single input x here, then we'll ensure that those Killian randomizations are all independent for this bucket, and therefore we'll be able to apply Killian's argument and information theoretically switch from an obfuscation of C0 to C1. The fact that it's information theoretic is a cool bonus. It's not necessary, but it's something that's cute and nice. I put a star here because in the paper we don't exactly do it this way, but this is what is going on. And just to illustrate this is kind of the moral lesson of this kind of a hybrid argument, is that suppose that I was implementing a particular program in this way, right? I take my input, x, I see if it's less than or equal to 37. If so, I evaluate C0 of x. I then check to see if it's less than or equal to 39, but I still just evaluate C0 of x. And otherwise, I evaluate C1 of x. Okay? Seems like kind of a weird artificial program, right? But if I can prove that this program is indistinguishable from this program, where I've just changed the threshold from 37 to 38, where both of them are still evaluating C0, right? All I did, it used to be the case that this part of the if was responsible for 38 and 39, and now it's only going to be responsible for 39, and we're going to move 38 to here. Right? That's all I did. But this seemingly little change is actually sufficient. That if we can handle these kinds of changes, these little rearrangements, sort of obfuscations, then we can actually leverage this to get all the way to I/O. Okay? All right. So how do we do it? So we start with our obfuscation, right? The one that we've talked about before. Okay? And first we just make a copy, right? So we just copy it over to another parallel obfuscation. I won't go into the details of that, but that's fairly simple, relatively simple. Okay? And again, these are both obfuscations of C0. They're completely identical, right? There's nothing different about the two circuits. They're randomized separately, but they're otherwise completely identical. Okay? And then in the key step, what I want to do is use that assumption, this multilinear subgroup elimination assumption, to bifurcate the inputs, right? I want to say that the inputs that start with x1 equals 0 are going to be handled by this obfuscation. The ones that start with 1 are going to be handled by this obfuscation. And intuitively, I do that just by zeroing out these matrices. Okay? So if I can do that, if I can go from this to this, right, then I have reallocated the inputs among these two obfuscations of the same function, right? That's going to be the key thing that I'm going to need to do. If I can do this, then it's actually very easy for me to carry out my agenda, right, of eventually isolating and moving things over, right? Because then I could make another copy, I could, again, do a similar step, and then I can keep doing this until finally I've isolated one input here, right? And once I've isolated it over there, then I apply Killian and switch it over to C1, just information theoretically, right? And now I've got this isolated, I've got another one, then I'll isolate one more, I'll switch that over to C1, and then I'll just combine these back, right? Using exactly the same argument. So in this way, it's sort of a tree traversal. You can just go, you can pebble your way through a tree with only a polynomial number of pebbles and eventually wind up until you've reallocated everything over to C1. Okay? And that's the overall idea of the argument. Does that make sense? Again, does it make sense that this would only require a polynomial number of buckets to do this? Because again, all of these steps are splitting in half, right? The inputs. And so this is still responsible for a huge number of inputs, right? And we can just leave them there until we get to one of those inputs to isolate. And in this way, yeah.
So all this is to sort of change one input from doing C0 to C1, right? And
exactly. Yeah, all this is just to isolate that one, right? That one input, which then we were able to then use Killian to switch it to from C0 to C1. And we just keep doing this dance. It's going to take 2 to the n steps, but eventually we'll get everyone over. And we'll only ever have something like 2n parallel obfuscations that will be required to do this. Okay, 2n plus 1, yeah.
So you formulate this transformation as something that goes from basic form of obfuscation to full obfuscation? Like instead of talking about the assumption, I don't know if you want to do it, but I think you could do it, right?
Yeah. That's what I got at with that example of the code, right? That you could actually just write it that way. That as long as you can do these kind of things, then together with Killian or an alternative to Killian that just allows you to do one input switching. You could use Yao, it doesn't matter, but you can then carry out this approach.
Right. Is it important that you're using only order over and parallel obfuscation instead of 2 to the n?
It's very important, right? Because if the obfuscation size grows exponentially with n, then it's trivial. I just write a lookup table, right? It's essential that the number of parallel obfuscations is only polynomial in the input size. Or polynomial in the original circuit size, but in our case, it'll just be polynomial in the input size. Does that make sense? Because again, we want the obfuscation itself to be efficient, right? If it has to create too many parallel obfuscations.
Also, the parallel obfuscations are happening in the obfuscation, not in the analysis.
Yes, sorry. Yeah, this is what the obfuscation actually looks like. Like at a certain point, the obfuscated in the hybrids, there will be an obfuscator that will output a single obfuscation that will have all these parallel obfuscations in one. Okay, and looking ahead, this will be like for the these different primes, the distinguished primes and the special primes and the other primes. They will correspond to these different obfuscations. This will be happening in prime C. This will be happening in prime A1. This will be happening like that. Okay. So it's very important that we only need a polynomial number of them. But again, it's just a simple tree traversal with pebbles that you need to. All right. So let me give you a little bit of a sense of how this magic works, right? How do we actually deactivate? So let's not talk about deactivating 2. Suppose I just have this one matrix here, and I want to deactivate it, right? It's okay for me to deactivate it because I have this redundant guy over here, right? He's anyway obfuscating the same circuit. So if I zero this out, I haven't changed anything, right? I haven't changed the functionality. So just at a very high level, thinking back to our multilinear subgroup elimination assumption, right? As I said, I need to have parallel obfuscations. I'm going to use the primes to do that, right? Now, what do I want to do? I want to be able to kill that one matrix, right? So it better be that this obfuscation is being done in the C subgroup, right? Because the C subgroup is the one that gets zeroed out in this transition, right? Either T has something in the C subgroup or it has nothing in the C subgroup. That's what we're going to use to indistinguishably zero out one of these matrices, okay? So we'll have the prime C over here. We'll have the other distinguished primes for the other guys that we have around. And as I said, we have to use this T to create these matrices, right? And the fact that they would, so remember, T always has an A1 component, so this guy will never be affected, but it either has or does not have a C component. So either that one will be there or it won't, which is exactly what we want to do. How do we do the rest of it? It's not so straightforward. It's a little complicated, but essentially that's why we have these HIs. These elimination guys, they basically allow us to create these straddling sets. The missing component is kind of related to the straddling structure that we want to implement to maintain the input, the security against input mixing attack. Yeah?
So when you say that a matrix is no longer there, like when it disappears from the circuit, what you really mean is it's been replaced by a random matrix? So that
No, it's been replaced by 0. It's been replaced by actually 0. Yeah.
So when the distinguisher can see the matrix 0 there.
No, so what will happen, right? The thing is that you'll multiply all these matrices according to the evaluation. This part will still either evaluate to 0 or non-zero, right? This part will always evaluate to 0 because it'll have a 0 matrix, but it's blinded by this one. So whether the output is 0 or non-zero is determined entirely by the circuit and not by what we're doing here. That's critical. And it comes up in how we build this. So yeah, once we've done that, again, the assumption exactly tells you that either T has this component or it doesn't, which means that I go from having the matrix there to having it zeroed out, right? So this is the idea, and a key point that allows this reduction to go through is that the programs, the underlying matrix branching program that we have for each individual prime is fixed. The reduction knows all the programs that are being obfuscated. It knows exactly which program corresponds to the prime 0, exactly which program corresponds to prime 1, et cetera, right? So it's interesting that this reduction actually knows everything about the program being obfuscated, right? The only thing it doesn't know is that one little bit of information about whether or not it's going to be active on a particular input or not, right? That's what I think is kind of cool about this reduction and what allows it to go through. All right, so with that, I've kind of given you a summary of where we are with respect to obfuscation constructions and security analyses right now. As different questions have alluded to, there's the other question of where we want to be, right? So, what do we have, right? We have a candidate I/O for NC1. That's what we just saw. And again, there is the CLT15 candidate map under which the assumption, is plausible, and you'll see more about that in the fellow talk and in Mehdi's talk at the June workshop. So I'm going to take this opportunity to plug the upcoming workshop. We can also do all kinds of interesting stuff. Once we have obfuscation for NC1, again, as Craig will tell you, we can do all kinds of interesting stuff. But in particular, we can use it to get I/O, right? So we can use I/O to get I/O. In particular, Craig will tell you tomorrow that once you have I/O for NC1, that together with the learning with errors assumption allows you to get I/O for all polynomial sized circuits. You can even go further. Once you have I/O for polynomial sized circuits and one-way functions, you can actually use it to get I/O for Turing machines as long as there's a bound on the input size. That's the current sort of state of the art in terms of how far we can go with I/O, starting with I/O for NC1 with standard assumptions. And this is based on a sequence of 3, well, not quite a sequence, based on 2 works that independently obtained this result with bounded memory, and then a more recent work that got rid of the bounded memory constraint and left with only the bounded input constraint. And Brent will talk about that at the June workshop. In fact, we can even achieve constant multiplicative size overhead. So I haven't talked about efficiency at all in this lecture, except for polynomial time. And it turns out that there's a lot of inefficiency here. Okay, so all these multilinear representations and and all of these things do incur a significant loss. But asymptotically, we can leverage I/O, leverage this hardness to even achieve a situation where the size of the obfuscation is just 2 times the size of the original Turing machine, plus some additive factors that don't depend on the size of the Turing machine. Those additive factors are 2 to the 100 something. Maybe. That's a very conservative estimate. I'm sorry. But it's cool that we can get asymptotically constant multiplicative size overhead. And Prabhanjan will talk about this at the June workshop, right? But of course, the elephant in the room is that these Mmaps are new. These assumptions are new. What can we do about that, right? And what can we do about it? Well, as Sanjam alluded to, right? Certainly, one thing that we can do is just gain confidence in these assumptions through an attack and defend cycle, right? This has been happening now in the multilinear map world over the last several months, and it's led us to this beautiful CLT15 construction. And certainly, we have a storied history of this in cryptography, block ciphers, in bilinear assumptions over specific elliptic curve families, and many other examples like that. We could reduce this multilinear subgroup elimination assumption to some nicer underlying assumption, right? Maybe based on some new candidate Mmap where there is some way of doing some other kind of reduction. That would be great if we could do that. And then finally, we can explore other completely new ways of building I/O, right? In ways that maybe allow for other nicer assumptions, right? And this is more speculative in the sense that we're not sure what it could allow means, but there's been some really exciting recent progress here in a paper by Prabhanjan and Abhishek that's going to be at Crypto, and an independent work of Nir and Vinod, which Abhishek will talk about at the June workshop. It was shown how to build I/O from compact functional encryption. I won't define that for you right now because I don't have enough time, but this gives a completely different way of achieving I/O. Unfortunately, currently the only way we can build compact FE is to use I/O. So right now it doesn't make any progress. It's using I/O to build I/O, but this could change in the future because again it's a different object, and we can hope to have different approaches to achieving this, right? So these are some ways forward, and I'm sure there are many other ways forward that I haven't thought of. If I have a little bit of time, I'll just give you a little ad for Abhishek's talk at the June workshop. So how does it work? How do you go from compact FE to I/O? So the starting point is a pair of papers on something called multi-input functional encryption, where in those papers we showed that MIFE implies I/O. Okay? And what these guys showed is that basically MIFE is the right induction hypothesis. Okay? That what you can do is you can start with something more basic, like private key functional encryption, public key functional encryption, these compact FE objects, and start to bootstrap up the level of multi-inputness of the functional encryption scheme. So you start here, you get MIFE2, then you get MIFE3, and you can keep on doing this until finally you get MIFE for n inputs, which then allows you to get I/O. And this slide was shamelessly stolen from Abhishek's excellent talk. You'll hear more about it in June. And the compactness issue arises in this level of iteration. So the fact that you can iterate this n times is because of this compactness requirement that is described. So, all right, before I end my talk, I wanted to just make one general observation, right? So if we think about the history of cryptography, right, we've been incredibly successful. I think we should all be very proud of what our community has accomplished, no doubt. But what are we leaving on the table? That's kind of the question I want to ask. This is not just about obfuscation, but in general, what are we leaving on the table? So what do I mean by that? Our table is cryptography, which for this slide, I mean hardness, right? Cryptography is all about leveraging and using hardness. So I'm ignoring information theoretic cryptography for now. No, not at all. Information theoretic cryptography is awesome, and we get to use all those cool tools like we just did. Like Killian's tool was an information theoretic tool which you got to use, right? But because it doesn't fit in the slide, I'm going to ignore it. So I have no greater reason than that. But it's really amazing, right, what we've been able to do. We started back in the 80s with some basic assumptions, GGHRSW factoring, and this beautiful world was built, right, with public key encryption, multi-party computation, zero knowledge, so much beautiful stuff, right? Back in the 90s, we saw this world and we said, wow, this is amazing, right? What more could you possibly want, right? And I remember Avi used to give this talk, where he really made it sound like crypto is solved, like they're just so, you start with these assumptions and we get these amazing results, right? But then, we got these bilinear assumptions, and we built more beautiful things, right? Identity-based encryption, attribute-based encryption, short signatures, much, 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 much more, right? Then we got Gentry's, ideal coset problem and LWE, which, gave us this amazing fully homomorphic encryption object, right? And now we have these Mmap candidates, which are giving us obfuscation, functional encryption, and crippleware, which maybe... okay, anyway, I won't promise anything on Craig's account anymore, right? But there seems to be a clear theme here, right? As we go, do we believe that we'll be able to get FHE from factoring? I don't know. I mean, it seems a little bit tricky, right? I can't say for sure the answer is no, but it seems like maybe not the right way to go, right? So our field has progressed in this amazing way by looking for new sources of hardness to leverage, right? And there's so much room on this table, right? The reality is we know hardly anything about hardness. I mean, of course, because we haven't resolved P not equal to NP, right? So we fundamentally know very, very little about hardness. But there is all this space on the table, right? And what else is there? How can we explore this? This is just sort of a question to think about. What's the right way to approach this kind of question? How do we systematically explore this table of hardness? How do we identify new interesting problems, new interesting sources of hardness, and figure out how to leverage it to get even more amazing things? Right? All right. So with that, I'd like to conclude. Obfuscation, despite amazing progress, is still in its infancy. I think we really need to explore risky new approaches, go out on a limb as we've been doing and get more understanding of what's going on here. I think if we eventually want to get to something like I/O from LWE, we need to take risks along the way to explore what the freedom of movement is here. As I've mentioned before, efficiency does remain a major bottleneck. I haven't talked about it at all today. 2 to the 100 is a conservative estimate on these additive overheads that are required. And then it's surprisingly useful, as you'll find out tomorrow. All right, thank you.
Any more questions here? So we didn't cover the space of hardness sources, but in terms of application, do we cover everything, or is there something beyond this last flower of obfuscation that we want to construct?
It's a great question. I don't know. What is the next big frontier, right, after obfuscation? I'm sure there are, right? It's a good question. But even for obfuscation, right, maybe there are other sources of hardness that we should be really looking at to get obfuscation. Maybe multilinear map candidates are not the right thing to look at. So I think it's a more general question of exploring and understanding the interplay of hardness in a cryptographical useful way.
Yeah, you know, has an answer.
Time travel.
Time travel, there we go. Yes.
Yes. I like your last slide about
The flowers.
Flowers growing.
Yeah.
But another way to look at it is like we started like with mathematics that was done 400 years ago. We used to refer to Gauss for factoring and computational number theory at the beginning of the last century, and then pairing, which was why, and this like the second half of the last century. And the feeling is that now we are building on problems that will be maybe investigated mathematically seriously in the next century. But it's a state of development.
Right. And I think there's an aspect to which aesthetics has really influenced the evolution of cryptography, which, while on the one hand I am a very happy participant of that, I like our aesthetics, but on the other hand it's something to reconsider, right? Is in a search for truth, how much should aesthetics play a role in guiding our field? So this is another sort of aspect to think about the future. Yeah.
So you said indistinguishability obfuscation does not imply hardness because it's through helix and pin.
Right.
So is it conceivable that you could have it unconditionally, or does it imply?
It would imply a collapse of the hierarchy.
Any more questions? Okay, let's think.
Yeah.
So there's something that bothers me, especially about your first construction.
Okay.
So the proof that you show, it really has nothing to do with I/O, right? I can substitute any definition which is weaker than VBB, and I can show the same proof for that.
Well, not exactly, because the proof I gave was only for I/O, but you're absolutely right that we can strengthen that proof to make it work for anything in VBB. That's exactly what Tal was asking earlier, right? Like, why should we pay any attention to that if you can prove VBB, which we know for certain cases is impossible? But again, as Yael mentioned, and as we talked about before, similarly, the situation is there for random oracles, right? Random oracles, there are negative results, right? If you say, well, if you're using a random oracle, why should I believe you at all, right? We know that random oracles are impossible. But nevertheless, we like random oracle proofs. Some of us, sometimes, but as a community, we should like them because they've been very, very, very successful, right? So in a similar way, this gets at some understanding of where the hardness is coming from, where security is coming from. All right.